Alright, so in this video we're going to go over chapter 12, which is analysis of variance, most commonly known as the Anova Test. That's analysis of variance. Well, so what are we going to do in this chapter? Well, so number one, don't be confused about what we're going to do here, because we are going to, in this case, compare 3 or more population means. And well, what we're doing in the test doesn't seem to really have anything to do with the term variance. Well, and the reason for that is because we are going to do the Anova test the short way, that is just putting the data in the calculator and obtaining the statistic value that then we are going to compare with a critical value, as we usually do in every single kind of hypothesis testing. Well, so far what have we done? Well, so for example, chapter 9, we did comparison for two sample hypothesis testing, in which we compare whether one mean was not equal to a second mean. We also compare whether mean 1 was bigger than mean 2 or mean 2 less than mean 1, etc. But in this case, this test was only limited to comparing only two sample distributions, So, but what if we want to compare more than two samples? Well, in that case, there has to be a test, and that's called the analysis of variance, or the Anova test. So, in this case, well, the null hypothesis will consist of assuming that all the means, as many as we have, as many as we can have, as many as we want to analyze, actually, they're all the same. But the alternative hypothesis, which, by the way, this has to be HA. The alternative hypothesis is to tell that at least one of the mean differs from the other ones. All right, so let's just to give you the bigger picture here. Well, suppose we have three different schools at which some exam or like the SAT, for example, is going to be applied, and we want to know whether the means at each school are different or they are the same. So of course it would be hard to make a census, because every single school will have too many students to make a census to collect data for the entire each school. So what we're going to do, for example, in this case, we're going to take a sample size of n equals 17 with a mean, for example, let me just, whatever that mean is, it doesn't matter. Okay, we're gonna go over an example, a more visual example with numbers, actually. Then we're gonna take a sample at the second school of n equals to 12. Actually, by the way, the sample sizes for from each population don't have to be the same. All right, and then x bar 2, well, whatever that is, we don't know right now, we don't care. And then we're going to take a third sample of n equals, I'm going to say 14, whose x bar 3 is unknown. And then we're going to compare. So just to give you a more solid example, well, let's see, let's consider the mean scores of a math test at 3 different schools. All right, well, so at the first school, the mean, the average of the test was 81. At the second school, the average x bar 2, denoted x bar 2, was 79. And at the third school, x bar 3 was 80. Well, so let's take the ho and the ha in this case. So for the ho, we're gonna say that the mean of the first population is equal to the mean of the second population and equal to the mean of the third population. And for the ha, well, at least one of the means differ. Alright. So, well, what's gonna happen here most likely? Well, in this case, most likely if we collect data like this, we're gonna lose the argument here. So in this case, most likely HO wins, because if you look at the numbers 81, 79, 80.5, well, those numbers are not too far from one another. Let's look at the second scenario then. Well, so we're going to consider the same x bar. Okay, x bar equals 81. X2 bar, well, the second school did really terrible this time. They got a 29. And x3 80.5. Well, so let's have a look. Let's take the ho and the ha. So the ho is that mean 1 equals to mean 2 equals to mean 3. But the ha is at least one of the means differ. What is going to happen in this case? Well, looking at this data, most likely if we perform the Anova test on this data set, the ha will win, because look at the huge difference. But again, well, keep in mind, if we go back to chapter 8, in which we learned for hypothesis testing for the mean, well, hypothesis testing rather for one sample, most likely this could be a potential or a possible type 2 error. All right, possible type 2 error. It's a potential error in which the null hypothesis wins, but could it be the case that the alternative hypothesis would have won? Well, in this case, we could have a possible type 1 error. And this is due to sampling error. You know, if you go back to the video in which we discuss hypothesis testing for one population, in this case, it is discussed the differences between these two types of errors. So in this case, well, recall that possible type of error 1, well, most likely sampling error. Well, in this case, what could have happened? Well, maybe they chose the worst student or the underperforming students for the test in the second case. Or what could have happened? Well, maybe something happened when they were taking the test. Maybe some fire, the fire alarm sounded or went off or something, and well, students after that couldn't concentrate anymore on the test. But yet they could have performed as in the first case. Well, possible type of error 2. Well, what was that type of error? Well, in this case, this error is produced because not the entire population was reached. So the only way to determine whether they are right or whether we are right, it's to reach the entire population. But again, we are limiting ourselves to samples. Alright, so this is pretty much the bigger picture of what we are going to do for the Anova test. Well, all we do is compare 3 or more means. What are we going to do? What are we going to use to perform the test? Well, so the Anova test, well, number one, the assumptions. The populations have distributions that are approximately normal. The populations that have the same variance or the same standard deviation. Well, in this case, we are not going to calculate any variances, any standard deviations. And the samples are simple random samples. Samples are independent, you know, like we mentioned, we took the samples from 3 different schools for the math scores. And the different samples are from populations that are categorized in only one way. Right? That's why we typically call this one-way ANOVA, or ANOVA of only one factor. You know, there's only one factor that we study here. Procedure for testing the to perform the Anova test. Well, so there's 2 ways actually. We're using the p-value as usual. For the p-value, well, as we did back in chapter, what was it, chapter 8, if the p-value is less than the level of significance, well, then reject the null hypothesis. But if the p-value is bigger than alpha, the level of significance, well, in this case we fail to reject. That's still hold the same way as we have done in all different kinds of hypothesis testing. Well, I will show you how to use the Anova function on the graphing calculator soon. Using the F statistic, so in this case we are going to introduce a new distribution. It's called this Nedeker's F distribution, which is a skewed distribution, very similar to the chi-square distribution that we discussed in chapter 11, all about chi-square distributions and variance tests. Well, if you recall, for most cases of the chi-square distribution, well, chi-square, let me write this down here. Chi-square most of the times had k-1 degrees of freedom. In this case, the degrees of freedom are going to look differently. In fact, we are going to rely in 2 different degrees of freedom. Degrees of freedom 1 and degrees of freedom 2. Okay, so degrees of freedom 1, when we are given the data, well, k is the number of samples that we take. For example, the number of schools in the previous example, well, was 3. And nt, the number total of data values that we have in all the samples. All right, so in order to find the critical F score, well, let me show you the table. So it's going to be table A5. Worth noting here, table A5. And you will find it as a separate document. So this is table A5. Numerator degrees of freedom, they call it, and denominator degrees of freedom. More easily, let's call this D2, and let's call this D1. Okay. So how to perform the test? So as usual, we're gonna draw an F curve, not a normal curve, not a T curve, not a chi-square curve, but an F curve, which, by the way, the shape of the F curve is very, very similar to that of the chi-square. So we're going to shade on the right side of the F score critical and compare with the F statistics from the calculator. And as usual, if our statistic value falls within the shaded region, well, we reject the null hypothesis. Actually, we reject the whole, not the half. Otherwise, we fail to reject the whole. All right. So let's do one example. So let's see example 1. The data set below. display the satisfaction ratings recorded by 15 customers from 3 different fast food chains on a scale from 1 to 10. Well, so we have this first column for customers from McDonald's. The second column displays the data for the level of satisfaction on a 1 to 10 scale for customers at Jack in the Box, and the last column for customers at In-N-Out. Perform a hypothesis test to determine whether there is a difference in the customer satisfaction ratings of the stores at an alpha 0.05 significance level. So what are we going to do here? So number one, we need to determine the value of k, which in this case is the number of samples. The number of samples. How many samples do we have? Well, in this case we have 3 samples: a sample from McDonald's, a sample from Jack in the Box, and a sample from In-N-Out. So k equals to 3. And then the total number of NT, the total number of data values, is all the numbers that you see here. So 1, 2, 3, 4, 5 customers at McDonald's, 5 customers at Jack in the Box, and 5 customers at In-N-Out. That means 15. Be careful, it's not the sum of all these numbers, it's the number of observations, which is 15. Perform a hypothesis test to determine, well, okay, we already say that. Well, the ho and the ha, they're going to be exactly the same. So mu1 equals mu2 equals mu3. And the alternative hypothesis is at least one of the means differ. Okay. So we need to calculate D1 and D2. So let's recall the formulas for D1 and D2. K minus 1, very similar to chi-square, only for one of the degrees of freedom, 1 less than the sample size. So that is 3 minus 1, which is 2. D2 is the total number of observations minus the number of categories, or the number of samples, in this case NT, which is 15, minus K, which is 3. So 15 minus 3, that's a 12. Now, how are we going to interpret the table A5? Well, so we're going to go to D2, where it's the number 12, and D1, where is the number 2. So D1, it's the second column, and actually let's state this right here: second column and 12th row. All right, second column, 12th row. So second column, 12th row. So the critical F score is 3.8853. All right, so let's go back to this. So let's draw as usual. This is our F critical. Our F critical of 3.8853. And we're going to shade to the right. By the way, this test is right-tailed. We're going to shade to the right, and then we are going to find our F statistic. How are we going to find that F statistic? Well, so we're going to go to the calculator. We're going to click Stat and Edit. So here I have already populated my calculator. So if you want to pause the video, be sure to have all your data in L1 for McDonald's, L2 for Jack in the Box, and L3 for In-N-Out. So be sure to have all the same data. Once you're done, click stat again, and then in this case, well, we're gonna go to test. Go all the way down until you get to the Anova test, the Anova function. Click enter. What are we going to do? Well, we are going to input by commas. So let me actually do it here. Well, I'm going to do it as a summary afterwards. Well, let me do second, and then I'm going to choose L1. Click L1, and it should be there. Be sure to put a comma in between, as it looks like right here, and then do second L2. Be sure to put another comma, and then second L3. Once we're done inputting the 3 columns, just close the parentheses and click enter. And it's going to do the one-way Anova test for us. In this case, well, there's 3 pieces of information that we need to look at. Well, so we need to find F critical. We already found it, so that's 3.8853. And the F statistic comes from the calculator, which in this case is notice we're rounding to 4 decimal places, 5.6207. So 5.6207, and the p-value right here is this number, in this case to 3 decimal places, 0.019. All right, so we're essentially done here. All we have to do now is determine whether the F statistic 5.6 is bigger than 3.8, and indeed it is. So F equals 5.6207. Because it fell in the shaded region, our conclusion is HO wins. Oh, HO, never mind. The HA wins. Reject the HO. Alright. What about the p-value? Well, put the p-value right next to the significance level of alpha 0.05. Well, in this case is less than or equal, and according to the criteria for that, well, if the p-value is less than or equal to alpha, reject the null hypothesis, right? Which is the same type of criteria that we have been doing. Alright, so that was one example. Let's do one more just so you can see how can examples be different. Well, the data set below displays the gas mileage for 3 different cars based on random samples. Honda Accord, well, and then we have five pieces of information. Corolla, 5 of them, but in this case Mazda 3, we have 4 of them. By the way, we don't have to have the same sample size, the same sample sizes for each sample. That's the good thing. If one variable is missing, then we are fine. All right, so when we do the test, you might want to do L1, L2, L3. All right, and let's state what K and NT are. So K equals the number of samples, and NT the total number of data set in the set, which in this case is 14. All right, 5 plus 5, that's 10 plus 4, that's a total of 14. All right, perform the hypothesis to determine whether there is a difference in gas mileage between the 3 car models at an alpha 0.05 significance level. So the whole mu1 equals mu2 equals mu3. The HA, on the other hand, at least one of the means differ. right? So let's calculate the degrees of freedom d1, k minus 1, which in this case 3 minus 1 again is going to be 2. d2, which is nt minus k, so that's a 14 minus 3, which equals 11. That means we go to second row of the table, second column, and 11th row of the table to get the F critical. So that's what we're going to do now. Well, so we're going to find our F critical, shade to the right because it's a right-tailed test. And let's find F critical using our table. So going to the second column and the 11th row. All right, so 11th row, second column, our critical value is 3.9823. And let's write it down over here, F critical 3.9823. Let's find the F statistic using the Anova test. All right, so well, in this case, well, I mentioned to put all these data values in L1, L2, and L3. However, to shorten, to make this video a bit shorter and not me doing all this calculation, all these inputs rather. Oops, second quit stat. I put all the values in L4, L5, and L6, and that's something you might want to do if you don't want to erase data every time. You might want to take advantage of all the L's that you are provided by the calculator. So L4, L5, L6, it's the same as doing L1, L2, L3. Just be sure that when you do the Anova test, be sure to link to the correct names of the L's. So I'm gonna do stat test Anova, and in this case I'm gonna do second L4 this time. I'm gonna put a comma, and then second again L5 comma, second L6, and no more comma right here. Well, just close the parentheses. So in these examples right here we only had 3 samples, but of course on the homework you're going to see something with 4 columns or even 5 or 6 columns. So all you do is just keep putting the L's, L, L7, L8, etc. All the L's that you need, that you put in the calculator in the data set. All right, so let's click enter to get the information. So in this case we get the F statistic of F equals to 5495, rounding to 4 decimal places, and a p-value of 0.013. Okay, and with this we're ready to just say that in this case we have enough evidence that there is a difference in gas mileage between the 3 car models, because our statistic value fell in the shaded region 6.5495. So in this case, reject as well, reject the whole. All right, we have sufficient evidence to support our claim. Now, putting together the p-value or right next to 0.05, which is alpha level, again is less than or equal to the p-value is less than or equal to significance level, which of 0.05. So this is it for this chapter. It's very short. It's again, it's all calculator. So again, just coming back to the original title of this section of this chapter, rather, ANOVA, analysis of variance. Well, the long way to do analysis of variance is by calculating a lot of standard deviations and variances, and then computing the F statistic by means of finding the variance, actually variance among the samples and variances within the samples. The process is really long and tedious, so we only limit ourselves to do it this way, just comparing means. I will attach another video I will actually give you, not attach, to give you the link of another video in which they go over one example the long way. Just watch it, but you will not, just know that you are not expected to do it the long way. Just use, in this case, well, summarizing this, what did we do? ANOVA, L1, L2, L3. That's all we have to do. Be sure, don't forget the commas, and don't forget to close the parentheses. Alright guys, so this is it. So I'll see you in the next video.